this lecture I will look into more detail into some of the distribution functions. Okay. I will talk about the binomial distribution function and then the Poisson distribution and then the Gaussian distribution. Okay. These are distributions that you encounter frequently in various problems. Okay. So, we will start with the binomial distribution. Okay. Now, in order to start this, let's take an experiment where there are only two possible outcomes. Okay. So, there is one outcome which you can think of as a coin toss. So, you have heads or tails. Okay. Now, but let us say this coin is not a very faithful coin. So, it is slightly biased. So, there is a probability of one of the outcomes. So, the probability of one outcome is p, okay, and the probability of the other outcome, okay, should be 1 minus p, because the sum of the outcomes should add up to 1. So, I am going to start with the binomial distribution. Okay. Now, imagine tossing a biased coin, such that in each toss, okay, probability of heads equal to p, probability of tails equal to 1 minus p. Okay. And if p equal to half, then it is an unbiased coin, but in general we will say p may or may not be equal to half. Okay. Now, now the question is, if the coin is tossed n times, what is probability of exactly m heads? Okay. So, we will call this p of m, okay, any m, okay, it need not be the first m, need not be the last m. Okay. Obviously, we will assume that m is less than n, okay, less than equal to n. So, p of m, okay. So, now, so you have to get m heads. Okay. So, so if you can write this in the following way. You can write this as p raised to m, and then you have to get n minus m of tails. So, the probability of tails of one tail is 1 minus p raised to n minus m. Okay. And this is the probability of getting m heads, this is the probability of getting n minus m, that n minus m of these outcomes are tails. Okay. But this is again for this is for specific m to be heads and specific n minus m to be tails. Okay. So, you have to multiply this by the number of ways you can choose m outcomes out of n, okay, which we want to be heads. So, this is multiplied by a factor of n factorial divided by m factorial n minus m factorial, which is the number of ways to choose m outcomes out of total n experiments, okay, and those m outcomes you are going to have heads. Okay. Now, this is referred to as the binomial distribution of m. Okay. So, the m is the variable that you are saying. So, the probability that you get exactly m heads, okay, or as I said, you need not be heads or tails, it could just be m of outcome 1 and n minus m of outcome 2. Okay. So, the important thing is only two outcomes. Okay. So, this is where the binomial distribution is used. Okay. And this is a very useful distribution. Okay. So, the quantity p is a parameter. Okay. So, this is a parameter of the binomial distribution. the distribution. Now these two p's are different. The p that I refer to here is the probability of m. This is the probability of exactly m heads. Okay, so these two are slightly different. Okay, so I am still using p for both of them, but this is a function of m. So what is the probability that you will get exactly 1 heads? Okay. So the probability that you will get that m, so then you just substitute m equal to 1, okay, and what you will get is you will get p times 1 minus p. Okay. So p times 1 minus p, 1 minus p raised to n minus 1 times n factorial divided by m factorial times n minus 1. So let me write it out. So probability of 1 is equal to n factorial divided by n minus 1 factorial p 1 minus p raised to n minus 1 is equal to n times p 1 minus p raised to n minus 1. Now you can also have a probability of 0 heads. Okay. So probability of 0 heads is just 1 minus p raised to n. Okay. So that means all the others have to be tails. So you have 1 minus p raised to n, and this is incidentally this is equal to probability of all n. Oh well okay. So probability of n heads is equal to, so again you will have 1 here, you will have p raised to n. Okay, so that is the probability of n heads. Okay, the last two are very intuitive ideas. Okay. So the binomial distribution is actually, I mean, though it seems like a very simple distribution. Okay. So binomial distribution has applications in what is called as a random walk, or this is model for diffusion. Okay, so random walk is a model for diffusion of particles. Okay, this is again very important in non-equilibrium transport. Okay, so the binomial distribution has a very important application. Okay, and it's generally you will see it in lot of places. I mean, you will see it sometimes when you are doing in statistical mechanics, we use the binomial distribution. Okay. Now what is the average value of m? Okay. So this will be given by sum over I equal to 0. Now m can take value of 0 to, it can go all the way to n. Okay, m p m. Okay. And this we can write as m times okay. So now if you want to evaluate this, okay, it takes a bit of work. Okay. But if you finally evaluate it, okay, you will get an answer. Okay, you will get this answer that this is equal to m times p. Okay, so just say evaluation is not straightforward. Okay, I'll just say that it is not straightforward. Okay, but what I want to emphasize is that it can be done. Okay, but it can be done. Okay. So, what I mean is, if you just look at this series as by itself, okay, it does not look like something that that you can get that result. Okay. But however, the idea is if you realize that this is part of a binomial, this is a coefficient of a binomial term. Okay. So, the idea is P of m is equal to n factorial divided by m factorial n minus m factorial p raised to m 1 minus p raised to n minus m. This is the coefficient of p plus 1 minus p raised to n. So, or rather one of the terms in binomial expansion of this. Okay. And what we immediately see is that this implies that sum over m equal to 0 to n p of m is equal to p plus 1 minus p raised to n, which is equal to 1. Okay. So, this is normalized. So, the way the probability is structured, you can immediately see that this is part of this binomial expansion, and so it is going to be normalized. Okay. And now, what is done to show, what you can do to show this next result, okay, is to show that what the idea is to show that average value of m equal to sum over m equal to 0 to n p of m times m, okay, and this is equal to m n factorial divided by m factorial n minus m factorial into average value of m is not m p, it will be n p, sorry, I made a mistake there. Okay. It should be equal to m n times p. Okay. Okay. So, this times p raised to m 1 minus p raised to n minus m. Okay. So, what you can show is that this is actually related to the derivative of the binomial expansion coefficients. Okay. So, the idea is suppose you set let us say set 1 minus p equal to q. Okay. And now you say that suppose you have p plus q raised to n. Okay. This is sum over m equal to 0 to n factorial divided by m factorial n minus m factorial p raised to m q raised to n minus m. Now, if I take d by dp of p plus q raised to n, okay, this is equal to sum over m equal to 0 to infinity. Now, you have n factorial divided by m factorial n minus m factorial, and you have m p raised to m minus 1 q raised to n minus m. Okay. And now, if I multiply this by p, so then what is done is to so suppose you multiply this by p, okay, then what you will get is that so p this is equal to okay. So, let me just work this out again. So, there should be a second term, okay, which comes from derivative of this with respect to p. Okay. So, I will just write that second term also. So, now I will get minus. So, I will have all this as it is minus n minus m p raised to m q raised to n minus m minus 1. Okay. So, that will be the other term. Okay. The minus term is there is because p is 1 minus q. Okay. And so, now if I multiply this by p, then what I will get is minus n minus m p raised to m plus 1 q raised to n minus m minus 1. Okay. So, what you can see is that left hand side should be 0, okay. Then you get exactly what we are interested in, which is the first term. Okay. So, that should be equal to the second term, okay. And so what you end up with is that you will end up with the average value of m is equal to sum over m equal to 0 to infinity n factorial divided by m factorial n minus m factorial times n minus m p into p raised to m q raised to n minus m minus 1. Okay. And now again you can, because you have this factor of n minus m here, okay, what you have to do is actually do a few more manipulations. Okay. So the first term is you can take the n p outside, okay, and then you will have 1. So, if you just take the n times p, so okay, so you multiply and divide by q. I can write this as okay. And now again this so what I have done is I have exactly got average value of m here. Okay. So now if I just take this to the left hand side, so this is exactly average value of m. So p is an additional p factor. Okay. So what I can show is that average value of m if I take this to the left hand side, times 1 plus p by q is equal to np by q, okay, and this is exactly equal to 1. Okay. This quantity is exactly equal to 1 because of the normalized distribution. So now what is this? This is p plus q divided by q, that is 1 by q. So therefore this implies average value of m equal to n times p. Okay. So it is a bit of work to show this average value of m, okay, but you can work it out. So the binomial distribution has mu equal to average value of m equal to n times p. This is a very intuitive quantity, because each time you can think of it as each measurement you make, okay, you are sort of you sort of p is a fraction of each measurement that you get m. So if you make n measurements, then the average number of times you get it should be n times that fraction. Okay. So now this trick that I used, where I took the derivative, okay, that can be used to calculate higher order moments also. So suppose you want to calculate the value of average value of m square, I would do the same thing, but I would take two derivatives, okay, and when you take two derivatives you will get a m times m minus 1, and you go through the same argument, you go through the same manipulations, and finally you will also end up with the average value of sigma square. Okay. So I will just mention that the standard deviation of the binomial distribution. Okay. So the standard deviation sigma is equal to n times p 1 minus p. Okay. So square root of this. So it is a little bit more work, but you can show this. So that is so much about the binomial distribution. Now binomial distribution, as I said, one kind of distribution that is fairly widely used. Okay. There are other distributions which are called the Poisson distribution and the Gaussian distribution, okay, which can actually be derived from the binomial distribution, okay, but I will do this as part of the next lecture. Okay. So I will conclude this lecture here, and in the next lecture we will talk about the Poisson and Gaussian distributions. Thank you.